For decades, Yellowstone was considered peacefully dormant, but now scientists have uncovered more than 86,000 hidden earthquakes pulsing beneath the surface, signals missed until a new digital magnifier rewrote everything we thought we knew. If these so-called small tremors are multiplying below a supervolcano famous for cataclysmic eruptions, what else is Yellowstone hiding, and what could its silent movements truly mean? The true story starts with the first quake you never saw. Yellowstone's secrets don't surface on their own. They are drawn out by a web of sensors, hundreds of seismic stations, each one anchored in remote forests, ridgelines, and geyser basins. Since 2008, this network has recorded every tremor, day and night, in a continuous digital archive stretching across 14 years. Some stations sit just a few kilometers apart, close enough to catch the faintest shudder from deep beneath the caldera. Others fill the gaps along the park's edges, tightening the grid so that even the smallest events can be triangulated with surprising accuracy. The backbone of this network is not just the number of stations, it is the detail in their records. Each sensor comes with its own blueprint, orientation, sensitivity, and a unique instrument response file. These technical fingerprints let scientists correct for local quirks, like a tilting mast or a snow-buried cable, so that data from one corner of Yellowstone matches the rest. Field engineers trek out in every season, swapping batteries, recalibrating sensors, and logging every maintenance hiccup. Their meticulous notes, down to the hour a station went offline, are folded into the master archive, ensuring that no blip goes unexplained. The result is a dataset both broad and deep. Waveforms from 2008 to 2022 capture everything from the thunder of herd migrations to the distant rumble of a magnitude 3 quake. But for years, the true story lay hidden in the static. Standard earthquake catalogs, built on classic detection methods, could only spot the larger jolts, those that rang out clearly above the background noise. The smallest events, buried in the digital hum, went unnoticed, lost between the cracks of older algorithms and sparse sensor coverage. None of this changed overnight. It took the patient layering of new stations, careful calibration, and relentless data preservation to build a foundation strong enough for breakthrough discovery. When new processing tools finally arrived, they had a goldmine to dig into. Hundreds of terabytes of continuous, high-quality seismic data, all stitched together by the work of field teams and network architects. That is how the invisible became visible, and how the first hidden earthquake in a swarm of 86,000 finally left its trace in the record. The seismic archive alone was not enough to rewrite Yellowstone's story. The real breakthrough came from a new breed of digital detective, a deep learning algorithm fine-tuned to separate true earthquakes from the constant static of the caldera. Developed by a small team of data scientists and seismologists, this neural network combed through 14 years of raw waveforms, learning to spot the subtle, telltale signatures of microquakes that had always slipped past human analysts and older detection methods. Classic approaches like STALTA, the old workhorse of seismology, could only catch the loudest events, those with clear, abrupt onsets. But Yellowstone's smallest earthquakes murmur beneath layers of geyser noise, footsteps, and wind. To train the machine, researchers fed it thousands of labeled examples, real earthquakes, false positives, and every flavor of background interference. The algorithm learned not just what a quake looks like, but what it does not. How to ignore the rhythmic thump of bison hooves or the hissing roar of fumaroles. Once the model was ready, it was unleashed on the entire Yellowstone archive. Each candidate event had to clear a gauntlet of tests. First, the deep learning detector flagged possible earthquakes by their unique waveform patterns. Then a benchmarking suite compared every detection against gold standard hand-picked catalogs and matched filter templates. Only those events that matched across methods and passed strict phase association checks made it into the final catalog. The numbers speak for themselves. Where classic STALTA catalogs topped out at around 34,000 events, the machine learning approach uncovered 86,000, nearly a 10-fold jump. Detection completeness dropped from magnitude 1.3 to as low as -0.7, revealing a hidden population of microquakes. In head-to-head tests, the algorithm achieved over 93% precision and 95% recall, meaning more than 9 out of 10 detections were genuine earthquakes, not just digital ghosts. False positives, once a constant worry, fell below 2% for events above the completeness threshold. Location accuracy improved too. With more events and better phase picks, scientists could relocate earthquake hypocenters with tighter uncertainty, mapping out swarms and fault segments in unprecedented detail. What once looked like isolated blips now resolved into dense, branching patterns, each one a fingerprint of shifting fluid or subtle tectonic stress. The digital magnifier did not just count more quakes, it transformed how Yellowstone's restless ground could be read, giving scientists a trustworthy, high-resolution catalog to probe what lies beneath. Yellowstone's ground does not just tremble, it breathes. The evidence comes from above and below, captured by two of the most precise measurement tools in Earth science, GPS arrays and INSAR satellites. Every day, a constellation of satellites passes overhead, bouncing radar pulses off the caldera. The returning signals, measured in fractions of a wavelength, reveal whether the crust is rising, falling, or flexing in between. Each colored fringe on an interferogram marks a tiny shift, sometimes just a few millimeters, sometimes much more. On the ground, GPS receivers anchored in bedrock keep their own silent vigil. They log their position with millimeter accuracy day after day, year after year, recording the park's slow-motion choreography in 3 dimensions. Between 2004 and 2006, these instruments watched as the caldera floor lifted by about 17 centimeters, nearly the height of a coffee mug over just 2 years. That is an average of more than 7 centimeters per year, an extraordinary rate for a volcanic system that, by most standards, is considered quiet. The uplift was broad, centered near the northern rim of the caldera, and mapped in vivid detail by overlapping INSAR images. Each new satellite pass added another ring to the bullseye, confirming that the ground was moving upward, not just shifting sideways or subsiding. GPS stations in the heart of the park echoed the satellite data, their vertical tracks stepping steadily higher through the interval, with error bars so tight that even seasonal snowpack or groundwater changes could not explain the trend. This was not a one-off event. The instruments have recorded cycles of uplift and subsidence over the past 2 decades, sometimes alternating year to year, sometimes holding steady for several seasons. The precision of the measurements leaves little room for doubt. INSAR can resolve changes as small as 1 millimeter, while GPS logs every subtle lurch or pause. When both datasets agree, satellites from hundreds of kilometers above and ground stations buried in the wild confirm that Yellowstone's surface is in constant, measurable motion. The patterns are not random. Uplift tends to cluster near the caldera's center, often aligning with the locations of deep earthquake swarms detected in the seismic record. Subsidence sometimes follows, as fluids migrate, pressures shift, and the crust relaxes. Scientists use these data to draw cross-sections through the caldera, mapping the depth and shape of the sources driving the motion. Every new fringe, every GPS spike, is another clue in the puzzle of what is happening beneath Yellowstone's surface. The numbers are clear. This is a landscape in motion, and the ground itself is keeping score. Beneath Yellowstone's restless surface, the real argument is not whether the caldera is moving, but why. Each new episode of uplift or subsidence draws scientists into a debate that cuts to the heart of volcanic hazard. Is the driver a deep pulse of magma, or something happening much closer to the surface? The answer shapes not only how Yellowstone is understood, but also how its risks are managed. 2 main scenarios compete for attention. The first points to a deep magmatic source, melt accumulating or shifting between 7 and 10 kilometers down. In this view, the ground rises as the magma body inflates, pushing the caldera floor upward like a slow-motion piston. This model fits with classic elastic deformation theory. Pressure builds in a buried chamber, the overlying rock stretches, and GPS stations climb. When the pressure drops, the ground settles back. The numbers support this idea. Volume change estimates from inversion models often match the scale expected from modest magmatic recharge, not a major intrusion, but enough to leave a measurable imprint. The alternative is a shallower explanation. Here, the focus is on hydrothermal fluids, hot water and steam circulating in the upper 1 to 3 kilometers of crust. As these fluids pressurize, perhaps after being trapped by a new mineral seal or by seasonal snowmelt, they can lift the ground in a more diffuse, patchy pattern. This is the poroelastic model, rather than a single deep piston. The uplift comes from many small pockets of pressurized fluid, each one nudging the surface above. These changes tend to be more transient, sometimes reversing within months or a few years, and often coincide with bursts of shallow seismicity or sudden hydrothermal explosions. Both models have their champions. Independent geodesists point out that the spatial distribution of uplift, especially when it shifts from year to year, sometimes favors a shallow, fluid-driven process. Others argue that the broadest, most sustained episodes, like the 17-centimeter rise observed from 2004 to 2006, are hard to explain without invoking deeper magma movement. Inversion results often land somewhere in between, showing that the true source depth may vary by episode, or even involve both mechanisms at once. The debate remains open, partly because each new dataset brings its own uncertainties. GPS and INSAR can pinpoint millimeter-scale motion, but translating that into a precise depth or cause requires assumptions about the crust's properties, the shape of the source, and the role of fluids. Pressure volume calculations can bracket the possibilities, but rarely settle the question for good. For now, the diagnostic reasoning remains a careful balancing act, with every new uplift cycle adding fuel to both sides. What is clear is that neither scenario rules out the other, and that Yellowstone's ground is shaped by a constant tug-of-war between deep magma and restless fluids above. Boiling water doesn't always wait for warning signs. On July 3, 2025, Black Diamond Pool in Biscuit Basin erupted without a hint of seismic buildup, hurling a column of muddy water a full meter into the air. The blast echoed across the closed boardwalks, but no visitors were nearby. Every trail in the area had already been shut down for the summer, a direct response to the surge in unpredictable hydrothermal activity the year before. Rangers and scientists arrived to find the pool's edge splattered with steaming debris, but the landscape itself barely changed. No crater widened, no trees toppled. It was a minor event by Yellowstone standards, yet forceful enough to remind everyone that even a so-called sleeping system can lash out with little warning. The mechanics behind these explosions are as unforgiving as they are sudden. Superheated water, trapped beneath clay and rock, flashes to steam the instant a blockage gives way. Pressure builds invisibly until the weakest point ruptures. Unlike volcanic eruptions, these blasts do not need fresh magma, just enough heat, water, and a sealed vent. The result is a shock wave that can toss boulders, shred boardwalks, and, in rare cases, leave craters tens of meters wide. Most pass without injury, but the risk to anyone straying off the path is real and immediate. Historic records include survivors who describe a wall of scalding mud erupting without warning, leaving burns and broken bones in their wake. The 2024 closure of Biscuit Basin was not a routine decision. Park officials weighed the evidence: a string of minor blasts, erratic temperature spikes, and a troubling gap in sensor coverage near the most active pools. The old monitoring stations, battered by acidic steam and shifting ground, had failed to capture the earliest signs of trouble. Only after the new seismic and acoustic sensors went online did the full scope of activity become clear. Even then, the raw violence of the July 3, 2025 event overwhelmed one of the new instruments, frying its circuits in seconds. Field engineers later recovered a melted housing and a memory card warped beyond repair, a reminder that Yellowstone's hazards are not always predictable or even fully measurable. For visitors, the lesson is written in every warning sign. Boardwalks exist for a reason. The ground may look solid, but a thin crust often hides boiling pools just below the surface. Rangers recount stories of tourists ignoring closures, drawn by curiosity or the promise of a better photo, only to encounter the very real danger of a sudden blast. In the wake of the 2024 and 2025 events, the park expanded its safety zones and launched new public education campaigns, urging respect for the unseen forces at work. The unpredictable violence of hydrothermal explosions may be rare, but when they come, they leave no room for second chances. Sorting out what Yellowstone's signals really mean takes more than a glance at earthquake counts or a single satellite pass. Volcanologists rely on a checklist, a diagnostic toolkit built from decades of research at restless calderas around the world. Each line on that list helps separate the signs of deep magmatic stirring from the surface chaos of hydrothermal unrest. The first question is always about the earthquakes. Are the swarms deep or shallow? Long-period events with their slow-rolling waveforms often hint at magma movement several kilometers down. Volcano-tectonic quakes, sharper and more brittle, usually cluster in the upper crust, sometimes linked to shifting fluids rather than rising melt. In Yellowstone, most swarms happen between 3 and 10 kilometers beneath the surface, with a mix of both types. Patterns matter. When a swarm lines up at depth and lasts for weeks, eyes turn toward the magma reservoir. If it is a patchy burst near the surface, especially after heavy rain or snowmelt, hydrothermal processes take center stage. Next comes ground motion. GPS and INSAR data are compared for both speed and shape of uplift. Sustained, broad inflation, like the 17 centimeters measured from 2004 to 2006, suggests a large coherent source often interpreted as magma recharge. Irregular, patchy uplift, especially when it reverses quickly, matches the signature of shallow fluid pressurization. Scientists plot these trends against the seismic record, hunting for time-lagged correlations. Did the ground rise before, during, or after a swarm? Is the uplift centered over deep earthquakes, or does it wander with the hydrothermal zones? Gas chemistry adds another layer. High carbon dioxide flux, especially when paired with sulfur dioxide or elevated helium-3 to helium-4 ratios, points to a magmatic source. In Yellowstone, direct sulfur dioxide emissions are rare, but carbon dioxide and helium ratios are tracked at key vents and springs. A sudden spike in magmatic gases, especially if it coincides with deep swarms and rapid uplift, would raise the alert. Instead, most gas changes here are modest, often tied to seasonal cycling or shallow boiling, not fresh magma input. Comparisons to other calderas sharpen the checklist. Campi Flegrei, near Naples, has seen uplift rates of 15 millimeters per year and swarms of over 1,000 earthquakes in a single season, but remains in a state of caution, not eruption. Long Valley in California shows persistent seismicity and carbon dioxide outgassing, yet its ground barely moves, and gas chemistry rarely hints at deep magma. Both systems, like Yellowstone, live in a gray zone, active, sometimes noisy, but not erupting. The diagnostic process is rarely clear-cut. Experts weigh each signal looking for clusters. Deep swarms plus sustained uplift plus magmatic gases would trigger concern. Shallow bursts, patchy motion, and modest degassing keep the focus on hydrothermal hazards. Yellowstone's current pattern, frequent swarms, cycles of uplift and subsidence, and steady but unspectacular gas output, lands squarely in the middle. The system is not dormant, but the checklist gives no sign of an imminent eruption. Instead, it points to a landscape shaped by both deep and shallow forces, demanding vigilance but not alarm. Yellowstone's restless ground, measured in thousands of hidden earthquakes and sudden hydrothermal blasts, reminds us that silence is not safety. With over 3 million annual visitors exposed to a living, shifting caldera, even subtle changes carry national stakes. Nature's warnings do not come with a timetable. Our challenge is not predicting eruption, it is choosing vigilance before the next sign becomes impossible to miss. What do you think? Are we listening closely enough?